what lies beneath our feet is vanishing silently. Wells are going dry, land is sinking, and billions depend on an unseen reserve that's running out. This is the groundwater crisis, and its story starts now. Beneath our feet, there has always been a hidden ocean smaller than the seas, but massive in scale. It sat quietly, stored in sands, gravels, and fractured rock, the groundwater that fed our wells, irrigated our crops, and kept rivers running in dry months. For decades, it was treated as infinite, a secret reserve to be tapped. Now, across continents, that secret is running out. The decline did not come with a single headline. It arrived incrementally, a meter here, a meter there, well after well drilled deeper, pumps running longer. The process has a modest name, drawdown, but its consequences are anything but modest. When water is removed faster than geology can refill it, the subsurface breathes out. Aquifers compact. Land subsides. Wells go dry. Why did this happen? The reasons are layered. Rapid agricultural intensification, urban growth, inadequate regulation, and an economic logic that subsidized pumping while ignoring recharge. The economics favored immediate harvests and short seasons. The hydrogeology recorded the debt in California's Central Valley. Millions of acres of high-value crops, almonds, pistachios, and citrus transformed a dry landscape into a global food source. Yet this productivity depended on deep groundwater. During drought cycles, farmers turned to their wells. Satellite radar later revealed the cost. Valleys sinking, sometimes several inches, 2 feet a year, permanently reducing the aquifer's storage capacity. Subsidence damages canals, ruptures pipelines, undermines roads, and raises the cost of moving water. It is the geologic proof of a hydraulic budget that no longer balances. Across the North China Plain and India's breadbaskets, similar dynamics played out, but at an even larger scale. High-yield crop varieties and subsidized electricity encouraged heavy groundwater pumping. In some regions, the water table dropped by tens of meters in mere decades. Villages once fed by shallow wells now depend on tanker trucks or distant municipal supplies. The social cost compounds: higher energy bills for deeper pumps, lost livelihoods, and migration from parched landscapes to already crowded cities. But groundwater is not only for rural life. Cities rely on deep aquifers for industry, construction, and often domestic supply. As urban populations expand, they place new demands on these subsurface reserves. This hidden extraction is rarely visible in municipal accounts. Private boreholes for construction sites, industrial wells for cooling, and informal water markets all draw silently from the same shared aquifers. The result is inequity. Where wealthier users can afford deeper wells or bulk water deliveries, poorer communities pay the price in dry taps and poor water quality. And not all depletion is simply a lack of water. As aquifers empty, the remaining water becomes more concentrated with salts and pollutants. In coastal aquifers, seawater creeps inland, contaminating freshwater lenses. In agricultural basins, nitrates and pesticides migrate downward with irrigation, rendering deep reserves unsuitable without costly treatment. This chemical decline makes the problem not only about quantity, but about quality. A dry well can be dug deeper. A saline well is a different kind of crisis. We are living in the age of measurement. Satellites, sensors, and well logs have transformed our view of the subsurface. For the first time, we can see drawdown across basins and continents. We can quantify how much water has been taken and at what cost. The numbers are stark. In many regions, recharge rates are a fraction of extraction. The arithmetic is simple and unforgiving. Behind each statistic is a person. We meet farmers who have drilled new wells only to find them dry months later. We meet women who spend hours at water kiosks. We meet communities negotiating informal rationing. Who gets water today and who must wait? The human toll is immediate and often invisible in macro policy debates. Economic incentives shaped this behavior. Subsidized electricity and water pricing that failed to reflect scarcity encouraged over-extraction. Weak regulation and fragmented governance left aquifers as a commons without strong custodianship, where groundwater is seen as private property rather than a shared resource. Coordination and long-term management are hard to achieve, yet policy can shift quickly when politics align. In some regions, meter installation and pumping fees have produced immediate drops in extraction. The question is whether short-term pain is acceptable for long-term survival. Groundwater decline echoes through ecosystems. Springs dry up, wetlands shrink, and the base flow to rivers decreases. Aquatic habitats contract, fish populations decline, and local climates warm slightly as vegetation stress increases. The loss is ecological as well as hydrologic. Technology helps reveal the problem and it can help solve it. Satellite gravimetry has mapped mass loss in aquifers. Low-cost sensors empower communities to monitor their own wells. This data transparency can catalyze local action when neighbors can see pumping rates, social pressure, and cooperative agreements become possible. But measurement alone is not a solution. It must be coupled with governance, finance, and incentives that align individual decisions with collective sustainability. Water stress drives migration. As shallow groundwater disappears, families move toward cities, increasing urban pressure on infrastructure. In some regions, scarcity intensifies resource conflicts between farmers and cities, between upstream and downstream users. While not always violent, these tensions make governance harder and the cost of inaction higher. The same technology that enabled intensification can also reduce demand. Drip irrigation, deficit irrigation strategies, switching to less thirsty crop varieties, and improved soil health that increases water retention. These changes require investment, information, and often changes in market incentives, but they can reduce extraction without reducing livelihoods. Some regions offer glimmers of hope. Managed groundwater associations that set extraction limits, trading systems that cap total pumping, and recharge programs that store floodwaters underground are all practical governance tools. They are imperfect, politically fraught, but effective where implemented with fairness and local buy-in. The problem is complex, but not insoluble. We will continue to examine the drivers: agriculture's thirst, urban demand, contamination, and then move to the solutions: managed aquifer recharge, water markets, nature-based systems, finance mechanisms, and community-led stewardship. This is not a single fix. It is a portfolio of tools that, together, can restore balance. Groundwater collapse is not a distant possibility. It is happening now, beneath our feet, and its effects will be felt for generations. The choice is stark. Continue to treat the subsurface as a limitless account to be drawn upon, or recognize it as a commons that must be replenished, respected, and managed. The months and years ahead will be decisive. The world that follows will depend on whether we learn to value what we cannot immediately see.